Hello everybody, Hobo here, and today I will be talking about the derivatives of parametric functions. Specifically, I will be talking about the first and second derivatives of parametrics, but before I begin, I will need to assume two things. First, that you have an elementary knowledge of basic differential calculus, and second, that you all know what parametric functions are, such as x is equal to f of t, and y is equal to g of t. And from here, I will be moving on to the derivatives of these parametrics. So, let's begin. In normal functional notation, when you have y is equal to f of x, we're used to seeing derivatives written as dy by dx. Now, what I'm asking is, what is dy by dx when I have some x is equal to, let's call this g of t, and y is equal to h of t. So, given these two parameters, I want to discuss what dy by dx of this entire parametric function here is. So, what we have to do is we have to include this. So we're basically talking about two variables only, x and y here, and we include the third variable which defines x. So let's begin. We have y is equal to f of x, and x is equal to g of t. So what we can do is substitute g of t directly into f of x, and then we get y is equal to f of g of t. And what I will proceed to do next is take the derivative of y with respect to t, which is my inner variable in here. And this is a composite function, so I will need to use the chain rule from calculus. So what the chain rule says is that if I take the derivative on both sides, then I will take the derivative of what's inside f, which is g of t, so that's x, and so that's going to be dy by dx, multiplied by the inner function, which is g of t, and what's the derivative of x? That's dx by dt. So, and now we have the thing that we're trying to solve for here, which is dy by dx. So we divide on both sides by dx by dt, and then we end up with dy by dx dx is equal to dy by dt, all divided by dx by dt. And this is wonderful. We've established the first derivative of a parametric function in terms of the parameter t. And now I will be moving on to the second derivative, but to prove the second derivative case, we will need to use this first derivative case, and I'll explain why. So when we have a second derivative, what we're basically doing is d by dx of dy by dx, that's right, dy by dx. And that's in normal functional notation, but if I'm trying to do parametrics, I can take this definition and plug it in for dy by dx. So then I end up with this is equal to d by dx of dy by dt, all of that divided by dx by dt. And now we're trying to differentiate with a different variable x on a function that's represented by a variable t. So it's essentially a composite function, and I'm going to have to use the chain rule again. So what I'm going to do, and I'm going to condense this into a simpler form, I'm going to take an example. Let's say we had d by dx of y of t. Then it's essentially implicit differentiation. So what you do is you do d by dt of y of t multiplied by dt by dx. And that's the chain rule. So what we can employ the same exact thing here. In this sense, this dy by dt by dx by dt is our y of t function. And we just have to multiply it by d by dt and dt by dx. And what's really wonderful about this is that it cancels out algebraically as well. I know this is probably improper, but it's very nice. We can just cross off that and we get our d by dx original back. But anyway, that's beside the point. So what we do here, the next step, is d by dt of dy by dt divided by dx by dt multiplied by dt by dx. And I'm going to erase our first derivative definition there. And now what we're going to do next is we're going to try and solve this portion of our expression. And, well, how would we do this? We have dy by dt as the numerator, and we have dx by dt as the denominator. So it's essentially differentiating u divided by v whole prime. And this is the quotient rule of calculus. If you're not familiar with this, I urge you to look it up in a common calculus textbook, and you will know what I'm talking about. So I'm gonna take u by v whole prime, because I'm taking the derivative with respect to t of this entire function. So then what I do is u by v whole prime is equal to u prime v minus v prime u, all of this divided by v to the power of 2. So that looks like a z, v to the power of 2. And I'm going to employ that over here. And from now, I'm going to scrap the dy by dt notation. I'm just going to do the y prime notation. So instead of expressing derivatives in this long format, I'm just going to express them as primes. So dy by dt, that's y prime, and this is going to be y double prime. So u prime is going to be y double prime multiplied by v, which is x prime, minus v prime, which is x double prime, times u, which is y prime, and all of this divided by v to the power of 2, which is x prime squared. And that's not x to the power of 12, that's x prime squared. And all of this into my dt by dx, which is essentially just dividing it by dx by dt. So divided by dx by dt. And what is dx by dt? Dx by dt is also x prime in my better notation. So x prime. And now we have x prime squared on the denominator, and we also have x prime. So our entire second derivative of a parametric becomes y double prime into x prime minus x double prime y prime. All of this divided by x prime cubed, because I multiply my x prime with my x prime squared. And this is my ultimate definition for the second derivative of a parametric function. Thank you very much, and goodbye.